and because we did not have to commit what is this n, we may try to apply it for different cases with n parameterized in different ways physically representing the different principles of conservation. As an example, we will start with the conservation of mass. So, in the fluid mechanics we will be discussing about 3 conservation principles in this chapter: conservation of mass, conservation of linear momentum and conservation of angular momentum. So, we will first start with the conservation of mass. So, conservation of mass. When we talk about the conservation of mass, what should be capital N? Capital N is what? What is the property that we are conserving here? Total mass of the system. So, capital N is equal to m, which is the mass of the system. So, what is small n? Is capital N per unit mass, that is. So, let us substitute that in the Reynolds Transport Theorem and write dm dt for the system is equal to okay. Now look into the left hand side. Left hand side represents what? Left hand side represents the time rate of change of mass of a system. What is the definition of a system? A system by definition is of fixed mass and identity. So, the mass of the system does not change, mass within the control volume changes because something across the control volume is entering and leaving, but when you are considering the system, it is as if it is a conceptual paradigm that you are considering all the mass which comes into your analysis, and that does not change. That may occur different positions at different times. Sometimes that mass is out of the control volume, sometimes it is inside the control volume, maybe again it is leaving the control volume going somewhere else. You are not keeping track of the mass, but it is a conceptual mass which is which is the mass that you are considering as conserved. So, that does not change with time. So, this is always 0 by the definition of what is a system. Okay. So, the integral form of the conservation of mass fundamentally is this one. This is very general, and it all depends on that the special cases depend on that what further considerations that we make. See, regarding the choice of the control volume, we have again remained very general. We have never committed that the control volume is stationary or fixed. That is why in fact this V relative we have introduced, so that even if the control volume is moving, it has no consequence, it can still be applied. The other thing is we have not committed that the control volume is non-deforming. Okay. That means what is the example of a deforming control volume? Let us take an example. Let us say that you have a balloon. Initially the balloon is very small, but you are pumping air into the balloon, so it is getting inflated. So, if you consider the control volume like this, which is like which is encompassing whatever air is there within the volume, then that volume is changing with time, right. So, this is if you consider that air within the volume as the air within the balloon as the constituent of the control volume, and the balloon is being inflated, then the volume of the control volume is a function of time. So, here you have this V as a function of time. This is an example of a deformable control volume. So, if you have a deformable control volume, that is also not ruled out here because we have not committed here that V is non-deformable. So, in the most general case, V may be moving and V may be deformable. Moving and deformable are two different things. When we say it is moving, it need not be deformable, it is like it may be moving like a rigid body, and when it is deformable, it might be locally stationary but deforming, and when it is moving and deformable it is the most general case, that is it might move as well as continuously deform. So, all those possibilities are there, and let us try to see that in such a simple case how we make an analysis. Let us say that we are interested to find out, let us say that we are given, let us consider maybe a simple problem related to this. Let us take an example that you have a balloon like this, there is a rate of mass flow of air into the balloon which is being supplied by the pressurizing mechanism. So, some air at a given rate of m dot in is entering the balloon. The state within the balloon is such that you have a density, it is considered that the property within the balloon is uniform. So, uniform property within the balloon is an assumption. Our objective is to find out what is the rate of change of volume of the balloon with respect to time of the balloon. So, how we do that? We use this integral form of the conservation, left hand side becomes equal to 0. What happens to the right hand side? Look into this term, integral of rho dV. When we are calling that, or when we are stating that it is uniform property within the balloon, that means what? The density is uniform, but it may change with time. We have earlier seen that uniformity does not ensure steadiness. So, rho in general could be a function of time, but at a given time rho is uniform everywhere. So, if at a given time rho is uniform everywhere, it may be possible to take the rho out of the volume integral, because this the integral is testing the rate of change within the volume. So, if you take rho out of the integral, then this term, this is only the first term, this becomes rho into the volume of the control volume, because if you take rho out of the integral of dV becomes the total volume of the control volume. And what is the remaining term? Plus. So, what does it represent? It is the net rate of flow of what? Here the quantity is mass. So, it is net rate of outflow minus inflow of mass. So, outflow is 0, there is nothing which is coming out, and what is coming in? So, outflow is 0 and inflow is m dot in. So, you have the differential equation relating the volume, density and m dot in this way. Now, you may simplify further if you assume that the density is not changing with time. Otherwise, you have to know that how the density is changing with time, and it is not a trivial situation. Density is definitely expected to change with time. So, if you consider that the density is invariant with time, it is not a very practical assumption, but at the same time you have to keep in mind that it is not a rigid tank. If it was a rigid tank and if you are supplying the air, what will happen? The density will increase with time always, but because it is a flexible balloon, then whatever mass is coming in, this balloon is getting adjusted to that. So, it might be possible that the density is changing, but changing only slightly. If it was rigid, that assumption would have been a very bad assumption, but because it is flexible, maybe it has capability enough to adjust to that. Whether it has capability enough to adjust to that, it depends on many parameters. It is actually one of the very toughest problems in mechanics, because it needs the understanding of what is the elasticity of the balloon material. So, based on that, how it adjusts to that change in terms of the new density within inside is something that may need to be looked into more carefully. But if you make an approximation that as if it is not only uniform, but also another assumption that rho does not change with time, rho is not a function of time, then it is possible to find out what is the rate of change of the volume of the control volume with respect to time, that is m dot in divided by the rho. So, at least we have got a fair idea that it could be a deformable control volume, and if it is a deformable control volume, it is not a very trivial thing to deal with. So, this the first assumption may not be bad, because if it is pumped well enough, it will assume a homogeneous distribution of the density quite quickly, but this is perhaps not a very correct assumption. It may be approximate, but it is not so good. So, we will leave apart the deformable control volume, and we will what we will try to do is we will try to now consider a special case of a non deformable control volume. So, we will make two important assumptions. First assumption is non deformable control volume to further simplify the equation. So, if you have a non deformable control volume, then what happens? See, now we are looking into a very important aspect of mathematics. You have the derivative outside the integral. Question is, can you take easily the derivative inside the integral? That is it permissible that you take this partial derivative, maybe partial or ordinary, whatever it is, this derivative within the integral sign? Yes or no? In general, no, because if this v is a function of this time, then in general no, but if this v is not a function of time, you can take this derivative within the integral. If this v is a function of time, then you can take that, but with an adjustment of certain terms, and that is given by the Leibniz rule for differentiation under integral sign. But when you are considering a non deformable control volume, we are easily able to take the time derivative within the integral. So, then our form becomes 0 equal to okay. Next we will make another assumption. The assumption is that the control volume is stationary or fixed, stationary control volume. So, if you have a stationary control volume, then what is the consequence? Consequence is v relative is equal to v. The relative and absolute velocity are the same if the control volume is not moving. So, then the equation becomes plus integral of rho v dot n dA. Okay. We may simplify this further by what understanding? By a very important but straightforward understanding that it is possible to express this area integral in terms of a volume integral by using the divergence theorem. So, the divergence theorem, what does it state? F dot with n dA over the control surface is equal to the divergence of f dV. So, this volume, the surface has to, the area has to be an area which is completely bounding the control volume, that is the only important assumption. F is any general vector field. So, here what is the f here? Rho into v is the f here. So, in this particular example f is rho into v. So, the next step is 0 is equal to integral of, now you write it, both are now volume integrals. So, this one plus okay. So, the next term has also become a volume integral. So, you are now left with what term? Integral of something dV equal to 0. The big question is, does it mean that the term in the square bracket which is the integrand, it has to be 0? Yes or no? In a special case maybe yes. So let us say that let us think of say a function, this a volume integral is a bit more general, let us consider a one dimensional case. Say you have integral of fx dx. If integral of fx dx equal to 0, can you say that fx equal to 0? In general obviously it may not be in a special case, like if you have say sin x type of thing. So let us say you have integral from 0 to 2 pi. So this area and this area are same and opposite. So the integral will vanish, but the function fx is not vanishing at all points within the interval. But you have to keep in mind that that is not for any arbitrary domain of the integral, domain of the integration, that is only for a particular limit. Here the choice of the volume, elemental volume, is not based on a particular domain, it is absolutely an arbitrary choice of an element within the total volume chunk. So you have to keep in mind that the difference between this case and this case is one very important thing. Here this dx is really restricted with the limits maybe 0 to 2 pi, but here this choice of dv is arbitrary, okay, that is a very important thing. Since the choice of the dv is arbitrary, then what does, where does it land up? If that is arbitrary, then if this has to be 0, then the integrand should definitely be 0, because it is for each and every arbitrary choice of the elemental control volume, and that means that you must have the integrand equal to 0. So it is not for a general like interpretation for any case, but it is an interpretation based on the arbitrariness in choosing the control volume. So with that understanding, now we get this form of the equation. You can recognize that this is the continuity equation that we derived in a different way earlier. So this gives you not only the continuity equation in a differential form as a special example, it gives you a kind of mathematical skill or understanding of how to convert an integral form into a differential form. So we started with the Reynolds Transport Theorem integral form, and we could show that we can come up with the differential form of the same conservation. So this is again representing the mass conservation principle, but in a differential form. So it is possible to convert one form to the other, keeping the physical meaning intact. So that is one of the important strengths of the Reynolds Transport Theorem, that it is possible to derive almost all conservation equations in whatever form you like by starting with the most general integral form of the Reynolds Transport Theorem. And as an example, we looked into the integral form of the mass conservation, and its corresponding differential form also we revisited, and we found out that it is possible to convert one form to the other. Now let us look into some more examples of the use of the integral form of the mass conservation equation. Let us say that you have a wedge shaped element like this with the axis oriented along x and y, and the velocity field is a 2-dimensional velocity field is given by, say, u is given by this, v is given by this one, and 2-dimensional w is 0. Let us give some names to the faces of the elements here. The objective is to find out that what is the volume flow rate through AC. The dimensions are given, let us say this is 1 meter or just 1 unit, all are given in some consistent units, say this is 2, these are given, okay. So what we also are assuming that V0 is a constant, it is not a function of any other variable that we are looking for. So, how should we proceed with this problem? Let us say that we are interested to use the integral form of the mass conservation, and that is one of the natural things that we should use here, because there are the 3 phases across which fluid will enter and leave. So, the net rate of transport should be given by the integral form of the mass conservation, that is you have dm dt for the system plus this for the control volume plus integral of rho the left hand side is 0, because no matter whatever system you are considering, it is by definition of fixed mass. The right hand side, because we are assuming that rho is not changing with time, neither the control volume is changing with time. So, what is our control volume? Let us say that this triangular shaped element is our control volume. So, whenever we are making a control volume analysis, it is important to identify what is the control volume that we are taking, because you may take different control volumes. Of course, for this problem this is an obvious choice of the control volume, but there could be problems where there could be many different choices of the control volume. So, the equations that you are writing should be pertinent to a particular control volume that you have chosen, and that should be clearly mentioned. So, this triangular shaped thing is a fixed control volume, the volume of that is not changing with time. So, it is not a deformable control volume, neither the density is changing with time. So, this term goes to 0. So, what remains is this net term, which is nothing but basically the net rate of outflow minus inflow of mass equal to 0. So, if rho is a constant, let us make a further simplification that rho is a constant, then this will boil down to basically integral of v dot n dA over the control surface equal to 0. And when we say v, here the relative velocity and absolute velocity are the same, because it is a stationary control volume, it is not a moving control volume. So, this now we may break it up into 3 parts, because the control volume has 3 different distinct oriented surfaces. So, you can write this as the sum of the effects of AB, BC and AC. So, for AB when you write, what should be this corresponding expression? So, let us identify that where is that AB. So, you are looking for this phase, you are interested to find out what is V dot n, integral of that over the entire area. So, one important thing is here n is not a variable, it is like a line oriented along y axis. So, n is a constant. So, for AB what is n? So, let us try to identify what are the normal directions for the different edges. Here the edges are all straight lines, so they have unique normal directions. So, let us say AB, what is the n for that? Minus I. Then BC, and AC. So, for AC let us say that this is the unit vector normal. So, this will have its components, let us say this angle is theta. So, if the angle between the normal and the horizontal is theta, then the angle between the edge and the vertical is also theta, right. That means you can say that n is definitely cos theta I plus sin theta j, where you have tan theta equal to 1 by 2. Okay. So, what will this imply? This implies that like you have identified the direction normals for all the faces, only thing you require is the velocity. So, the velocities for the faces, for AB what is V, let us write the in the same table, let us try to write what is the velocity V cap. So, for AB what is V cap? For AB x is 0, so u is not there, there is some V. Okay. So, it is minus V0 y by L j. For BC similarly you have y equal to 0, so it is V0 x by L I, and for AC it is the real the sum of the two components, because here x and y are both non-zero. So, we are not writing it because it is like let us just write it as in general ui plus Vj. Now, to get the integral you have to keep in mind that if the velocity varies along that length, then you have to integrate it over the length to get the total flow rate. When you come to the, so let us start with AB. You can of course evaluate this, try to evaluate this, but let us not do that bulwark. You see that the velocity along AB is like it is oriented along AB, so there is no normal component of that. So, there is no net flux or influx or outflux of flow across AB, because there is no normal component. So, if you make a dot product of this, that you can clearly make out, and so that will not give rise to any net flow. Same might be true for BC, right. So, the choice of the axis here has been such that if this is the velocity field, then that is the case, but the same is not the case for AC, right. So, for AC how will you find out what is the total or the net rate of flow? Yes. So, if something there is nothing that enters here, there is nothing that enters or leaves here, you expect that there is nothing enters or leaves here, right. How could you verify? By doing the integral that it should be 0? No, that is what, like this is QAB, this is QBC, this is QAC, like if you evaluate by doing the dot products, will the dot product automatically give it? It is expected that the dot product to integral over that should automatically give it. So, that you should check, so that it gives you a confidence of how to calculate that, because here I have given a special type of velocity field, so that actually this problem solution is not necessary. I mean, I am trying to go through this through a formal route to give you an idea of what should be done in a case when the problem solution deserves that, but here actually it does not deserve. So, this is a more intuitive case where nothing is entering and nothing therefore is expected to leave. Now, If by chance you get something which is leaving through this and nothing is entering, so that will really violate the law of mass conservation. So that one has to be careful of. Now let us look into some other problem which is not as trivial as this one. So another example. Let us say there is a tank like this, the velocity profile at the exit of the tank is through this pipe is given by this one, and in terms of a local coordinate system, this let us say that the local coordinate system is x1 y1, it is given as u1 is equal to some u0 into 1 minus y1 by y1 square by h square, where y1 is the transverse coordinate and h is this height, and the fluid entering here, here the again in terms of the local coordinates you can specify it, but that specification may not be necessary because it is given that it is a uniform velocity profile here with a velocity u infinity which is uniform, and let us say this is h by 2. Okay. The directions of the axis are not given, that means it is not given that what is this angle theta, say theta 1, it is not given that what is this angle say theta 0, these are not given. What is given? It is given that the density is a constant. You have to find out what is u naught. Given the width of this figure perpendicular to the plane where it is drawn is uniform. Okay. So u infinity is given, h is given, these two things are given. Okay. So how will you go about it? Again looks like a situation where mass conservation should be applied, and if you want to apply the integral form of the mass conservation, let us say that we consider a control volume. So what should be a good choice of the control volume? So a good choice of the control volume is something where across the surface we are totally confident about the velocity field. So let us say that we make a choice of the control volume something like this. So with this choice of the control volume, you can write the law of mass conservation. If you want to write that, then like it is because rho is a constant, again it will boil down to a case very similar to the previous one, where eventually it will be integral of v dot n dA over the control surface equal to 0. The remaining terms will not be relevant. So, this is the only term that is relevant. Now, out of the surfaces that you have, only you have one inflow and one outflow surface, across the other surfaces fluid is not flowing. So, those surfaces are not relevant. So, you may break it up into two integrals, one for this inflow and another for the outflow. Okay. So, the first one is very straightforward, let us do that. So, when you have the v dot n dA, see this v is uniform over the area over which it is flowing for the inflow. So, you can take away this v out of the integral, not only that, the dot product also, because n is also a constant here. So, v dot n entire thing you can take out of the integral. So, what it will become? It will become v dot n into area of the face over which it is coming. So, let us call that this area of the face is a here a naught, and here the area of the face is say a1. So, when you write v dot n, you have to keep in mind that what is the direction of n in along this surface. So, the direction of n is opposite to v, right. So, v dot n will give the minus of the magnitude of v. So, for the area 0 or area O, it will become, this term will become what? Minus u infinity into h by 2 into the width. Let us say b is the width perpendicular to the plane of the figure. Then the other area for a1 we cannot have the same consideration because the velocity varies over a1. So, to see how the velocity varies with a1, we are along a1 we are already given that with respect to the local transverse coordinate how it varies. But n is a, but you have to keep in mind that forget about that functional dependence on y1, u1 is going out of the area, and what is n? N is also oriented out of the area. This means that if you just take the vector sense v dot n, that will give you the magnitude of v into 1, because the dot products are in the same dot products of two vectors in the same sense, that will be leading to that conclusion. But because it is varying with y1, now you have to really do the integration. So, when you first have v dot n, that will become u0 into 1 minus y1 square by h square, that will be v dot n, and dA is what? Say you take a small element on the axis y1. So, this is the small element of the area. So, what is that small element of the area? Say at a height y1 from the center line, see the coordinate system is from the center line. So, at a height y1 from the center line, say you have taken a small area of width dy1. So, the elemental area which is like the dA given symbolically, it is dy1 into b. If you integrate that from minus h by 2 to h by 2, then that will represent that what happens, for the area 1. So, sum of these two should be equal to 0. Clearly from the minus sign of the first term you can make that it is inflow, and the plus sign of the second term means that it is outflow, and it is possible to complete this integration in a very simple way. We are not going into that, just to save some time, but important thing is that see this is the variation of u over the section. So, you can write it equivalently as integral of u dA in the fundamental form in a scalar form. So, this is not like a vector form. So, it is like just like, because eventually with the dot product it has become a scalar. You have to keep in mind this u is nothing but the component of velocity which is normal to the area. Here fortunately all component is normal to the area, there is no component which is cross that. So, this you may express through some quantity which is called as average velocity. So, average velocity is this divided by the area. That means if this velocity was uniform but the same flow rate was there, see if it was uniform then that uniform velocity times the area will give you the flow rate, that is what the first term has told us, and if it is not uniform obviously you have to integrate it to get the flow. So, if the flow rate were uniform in a hypothetical case, sorry, if the velocity profile was uniform in a hypothetical case but the flow rate becoming still the same as it is in the real case, then if you equate those two flow rates then that equivalent hypothetical uniform velocity, this is called as average velocity. So, it is like a equivalent uniform velocity that would have prevailed across the section, satisfying the same volume flow rate as it is there in the real case. So, therefore, this is like as good as some u1 average into a1, and this is just like u naught into a naught. So, it is just like a1 v1 equal to a2 v2. You have to keep in mind again that what is v1 and what is v2, these are very important. Again I am repeating, these are fundamentally the average velocities over the sections 1 and 2. See, when we are writing here 1 and 2 or maybe 0 and 1 or whatever subscripts, there is a fundamental difference from what we wrote for using the Bernoulli's equation. Those we wrote for points 1 and 2. Now we are writing for sections 1 and 2. So, maybe subscript wise they look very similar, but meaning is entirely different. When it is uniform it does not matter, it is as good as writing for a point because velocity does not vary from one point to the other, but you do not have anything called as area at a point. So, it is basically when you write a1, no matter in the context of what we write what we have written earlier for 2 points, when we use the Bernoulli's equation we should keep in mind that there also a1 was for the section that contained the point 1. So, it is not that area of a point 1 or something like that, but there we use velocity at the point 1. The reason is that in the Bernoulli's equation we use velocity at a point. So, we had to link it with velocity at a point. Now, it is like we are linking things through velocity over an area. So, if you complete this problem you will get what is u naught because all other things are known.